January 17, 1944, Rogers Dry Lake, California. The sun had barely cracked the horizon when the stillness shattered. Across the pale alkali flats of the Mojave Desert, a sound unlike any heard before tore through the cold morning air. Not the familiar growl of a radial engine or the whistle of a diving fighter, but something altogether alien. A sharp, penetrating scream that seemed to cut the atmosphere itself. Mechanics standing near the flight line pressed their hands to their ears. A jackrabbit, startled from the sagebrush, bolted across the hardpan in panic. And then it appeared, a sleek shape with impossibly short wings, painted in experimental silver, streaking across the lakebed at a speed that made veteran test pilots shake their heads in disbelief. The aircraft was the XP-86 Sabre prototype in its earliest configuration tests. But this moment was not about the Sabre alone. This was the culmination of an American obsession that had begun years earlier, an obsession the enemy could not comprehend, rooted in a philosophy the enemy did not share. Speed, not merely as a tactical advantage, but as an engineering faith, a belief that the laws of physics were not barriers but puzzles, and that American ingenuity, fueled by American resources and American freedom of thought, could solve them faster than any authoritarian regime could mandate solutions from above. In the frozen skies over Europe, Luftwaffe pilots were already beginning to whisper about the American fighters, the Mustangs, the Thunderbolts, the Lightnings, that came not in ones or twos, but in formations of hundreds, all of them fast, all of them relentless. But what they did not yet know, what their intelligence officers could not yet grasp, was that America's pursuit of speed was accelerating beyond their comprehension. While German engineers were perfecting jet engines under the frantic pressure of a losing war, American engineers were calmly, methodically building something that would make those jets obsolete before they ever achieved numerical superiority. The pursuit of speed had become America's secret doctrine, and the machine on that lakebed was its prophet. To understand why one fighter's speed broke all records and shattered an enemy's understanding of possibility, you must first understand the world as it existed in 1940. In the spring of that year, Europe was falling. Poland had been crushed in weeks. Denmark and Norway had surrendered. France, the great military power of the previous war, was collapsing beneath the mechanized onslaught of the Wehrmacht. Britain stood alone, her skies contested daily by swarms of German bombers and fighters. And across the Atlantic, America watched with a mixture of horror and grim calculation. American military aviation in 1940 was, by any honest assessment, mediocre. The standard Army Air Corps fighter was the Curtiss P-40 Warhawk, a competent aircraft by the standards of 1938, but already obsolescent by the standards of 1940. Its top speed barely exceeded 350 miles per hour. Its rate of climb was sluggish. Against the German Messerschmitt Bf-109, it was outmatched in nearly every performance category. Against the Japanese Zero, which would soon reveal itself in the Pacific, it was dangerously vulnerable.
But America possessed something Germany and Japan did not: an industrial infrastructure not yet scarred by war, a pool of engineering talent not yet drained by casualties, and a philosophical approach to problem-solving fundamentally different from that of its adversaries. German aviation advanced through brilliant individual insights imposed from above. The Messerschmitt 262 jet fighter was essentially Willy Messerschmitt's vision, forced through bureaucratic resistance by sheer force of will. Japanese aviation advanced through meticulous refinement of existing designs, a cultural preference for perfection over innovation. American aviation advanced through something altogether different: organized chaos. Dozens of aircraft companies competing for contracts, university research labs collaborating with private industry, test pilots and engineers arguing in hangars and hotel bars, failures analyzed without punishment, successes rewarded with expanded budgets. It was messy, inefficient, and staggeringly productive. The pursuit of speed became the organizing principle of this chaos. In 1940, the National Advisory Committee for Aeronautics, NACA, the predecessor to NASA, established a singular priority across its research facilities: reduce drag, increase thrust, push the boundaries of what propeller-driven aircraft could achieve. At Langley Field in Virginia, engineers built wind tunnels capable of testing airframes at speeds approaching 500 miles per hour. At Wright Field in Ohio, propulsion specialists worked with Allison and Pratt & Whitney to extract more horsepower from every cubic inch of engine displacement. And in California, at the nascent facilities that would become Edwards Air Force Base, test pilots began flying experimental aircraft to the edge of their performance envelopes and beyond, documenting every vibration, every flutter, every aerodynamic quirk that might be solved. The goal was not simply to build a faster fighter. The goal was to make speed itself an American advantage so overwhelming that it would compensate for any numerical inferiority, any initial lack of combat experience, any geographic disadvantage. Speed meant you chose when to engage. Speed meant you could strike and escape before the enemy could react. Speed meant your bombers could outrun interceptors, your fighters could chase down anything that flew, your pilots could survive mistakes that would kill a slower opponent. This was the doctrine being forged in California wind tunnels and Midwestern engine shops while Europe burned. But doctrine means nothing without a machine to embody it. The Luftwaffe pilot's name was Hauptmann Klaus Richter, and in the winter of 1944, he was already a ghost. Not literally, not yet, but in the sense that he knew he was flying for a nation that had already lost the war. The tide had turned at Stalingrad. The skies over Germany were filled each day with American bombers flying so high and in such numbers that even the new Focke-Wulf 192s could barely intercept them all. And now, increasingly, those bombers were escorted all the way to their targets and back by American fighters with a range and performance that defied everything Richter had learned at flight school.
On February 8, 1944, Richter was scrambled from an airfield near Magdeburg to intercept a formation of B-17 flying fortresses returning from a raid on Brunswick. His Bf-109 G6 was a good aircraft, perhaps the best conventional fighter Germany had produced in meaningful numbers. It could reach 386 miles per hour in level flight, could climb at 3,000 feet per minute, could turn tightly enough to stay on the tail of most Allied fighters if flown by an experienced pilot. Richter was an experienced pilot. He had 23 confirmed kills. He had survived 3 years of combat over France, Britain, Russia, and now the skies of the fatherland itself. But when he climbed to 25,000 feet and spotted the American formation, he also spotted their escorts. At first, he thought they were P-47 Thunderbolts, big, powerful fighters that had begun appearing in large numbers in recent months. But as he approached, he realized these were different, sleeker, more graceful. They had the long, elegant nose of an inline engine rather than the blunt snout of a radial. And they were fast, impossibly fast. Richter selected a target and dove from above, the classic advantage of altitude converted to speed. His 109 accelerated smoothly past 400 miles per hour in the dive. He lined up one of the American fighters in his gun sight, squeezed the trigger, saw his cannon rounds arc toward the target, and the American simply accelerated away. Not dove, not turned, just pushed the throttle forward and pulled smoothly away from Richter's diving 109 as if the German fighter were tethered to the sky by invisible chains. Richter would survive the war and tell this story to American interrogators in May 1945. "I did not believe it was possible," he said through a translator. "I was diving, you understand. I had gravity and full power, and this American fighter accelerated away from me in level flight. For a moment, I thought perhaps my engine had failed. But no, my instruments were normal. It was simply that he was faster than physics should allow." The aircraft Richter had encountered was the North American P-51 Mustang.
and it was not even the fastest fighter America would field before the war's end. The Mustang story begins with a problem and an insult. In April 1940, the British Purchasing Commission approached North American Aviation with a request to build Curtiss P-40 fighters under license for the Royal Air Force. Britain needed fighters desperately. The Battle of Britain was months away, and American industrial capacity was the only source that could supply them in adequate numbers. James Dutch Kindleberger, the president of North American Aviation, made a counter-proposal that bordered on audacity. Instead of building an existing design under license, he suggested, why not let North American design an entirely new fighter from scratch, incorporating the latest aerodynamic research and building it around the new Allison V1710 engine? It would take only 120 days to produce a prototype. It would be faster, more efficient, and more effective than the P-40, and it would cost the same price per unit. The British agreed, perhaps because they had little to lose. North American had never built a fighter aircraft before. If the project failed, they could always fall back on licensed P-40 production. It did not fail.
On October 26, 1940, exactly 102 days after the contract was signed, the first prototype rolled out of North American's Inglewood, California factory. It was designated the NA-73X. It had a sleek, streamlined fuselage built around the principle of laminar flow, a design philosophy that minimized drag by maintaining smooth airflow over the wing surfaces. It had a low-drag radiator scoop positioned beneath the fuselage, turning the cooling system into an additional source of thrust through the Meredith effect. It had a lightweight structure that maximized speed and range without sacrificing strength. When test pilots flew it, they reported handling characteristics that were almost dreamlike, responsive, forgiving, stable at high speeds. It was, by virtually every measure, the most aerodynamically refined piston engine fighter anyone had yet built. But it had one critical flaw: the Allison engine. At low altitudes, the Allison V1710 produced respectable power, but above 15,000 feet, its performance dropped off sharply. Since most air combat in Europe occurred above 20,000 feet, this made the early Mustang, designated the P-51 and P-51A, unsuitable for high-altitude escort duty. The Royal Air Force used them primarily for low-level ground attack and reconnaissance. The U.S. Army Air Forces showed little interest. The breakthrough came in 1942 when a Rolls-Royce test pilot named Ronald Harker flew a Mustang and immediately recognized its potential. This aircraft, he wrote in his report, would be transformed by the installation of a Merlin engine. The Merlin, the same engine that powered the Supermarine Spitfire and the Avro Lancaster bomber, was a supercharged masterpiece that maintained high power output at altitude. When North American engineers mated the Mustang airframe with a license-built Packard Merlin engine, the result was a fighter that could reach 440 miles per hour at 25,000 feet, could fly escort missions all the way from England to Berlin and back, and could outmaneuver or outrun virtually any opponent it encountered. By early 1944, Mustangs were arriving in Europe in massive numbers, and Luftwaffe pilots like Klaus Richter were learning a bitter lesson. No amount of skill or courage could overcome an enemy who was simply, fundamentally, faster. But the Mustang, for all its brilliance, was not the absurd machine that broke all records. That distinction belonged to a fighter born not from British contracts or European necessity, but from a uniquely American competition between rival engineering philosophies. A competition so intense and so personal that it would produce two of the most extreme aircraft of the war. In 1942, the U.S. Army Air Forces issued a request for a high-altitude interceptor capable of escorting bombers deep into enemy territory and engaging enemy fighters at altitudes above 30,000 feet. The performance requirements were staggering: a top speed exceeding 400 miles per hour, a combat radius of at least 750 miles, a ceiling above 40,000 feet, and armament sufficient to destroy heavy bombers.
Two companies submitted radically different proposals. Republic Aviation proposed what would become the P-47 Thunderbolt,
a massive, heavily armed fighter built around the most powerful engine available, the Pratt & Whitney R2800 Double Wasp Radial. Lockheed proposed what would become the P-38 Lightning, a twin-engine, twin-boom design that looked like nothing else in the sky. Both were exceptional aircraft, but neither was absurd. The absurd machine came later, from a competition nobody asked for. In 1943, as American forces prepared for the final campaigns in Europe and the long island-hopping advance across the Pacific, military planners began contemplating the next generation of fighters. Jets were on the horizon. The Germans were already flying the Me-262 operationally. But jet technology was still immature, unreliable, and fuel inefficient. What if, planners asked, you pushed piston engine technology to its absolute theoretical limit? What would that look like? The answer came from Republic Aviation, the same company that had built the 7-ton Thunderbolt. But this time, Republic's chief designer, Alexander Kartveli, took the opposite approach. Instead of building bigger and heavier, he decided to build smaller and lighter. Instead of maximizing firepower, he decided to maximize speed. The result was one of the most unconventional American fighters ever designed, the Republic XP-72. It looked like a Thunderbolt that had been stretched and compressed simultaneously. A longer fuselage, a massive four-bladed propeller, and an experimental version of the R2800 engine equipped with an advanced turbo supercharger that could deliver 2,800 horsepower, nearly double the power of a standard Thunderbolt. The entire aircraft was designed around one singular goal: speed. On February 8, 1945, exactly 1 year after Klaus Richter's encounter with the Mustang, test pilot Mike Ritchie climbed into the second XP-72 prototype and took off from Republic's Long Island facility. He climbed to 25,000 feet, leveled off, and pushed the throttle to maximum power. The XP-72 accelerated like a dragster. The needle on the airspeed indicator climbed past 400 miles per hour, past 420, past 440. At 450 miles per hour, Ritchie felt the aircraft begin to buffet slightly, the first hints of compressibility effects as the propeller tips approached the speed of sound. He held the throttle forward, 460 miles per hour, 470. At 480 miles per hour, the buffeting intensified, and Ritchie eased back slightly. He had just achieved the fastest speed ever recorded by a production-designed piston-engine fighter. The XP-72 could reach 490 miles per hour in level flight at optimal altitude, faster than most early jets, faster than anything Germany or Japan could put in the sky, faster than seemed reasonable for an aircraft with a propeller. But by the time Mike Ritchie landed that day in February 1945, the war was already ending. Germany would surrender in 3 months. Japan would surrender in 6. The age of the jet had arrived, and the XP-72, for all its astonishing performance, represented the end of an era rather than the beginning of one. Only 2 prototypes were ever built. Neither saw combat. The program was canceled in 1946.
But the XP-72's brief existence proved something the enemy had never truly understood: that American engineering, freed from the constraints of authoritarian rigidity, could pursue ideas to their logical extremes, even when those extremes had no immediate practical application. The XP-72 was absurd, not because it failed, but because it succeeded so completely at solving a problem that no longer needed solving. It was a monument to excess, and in that excess lay a truth about American industrial and intellectual philosophy that no propaganda could convey. Japanese pilots experienced this truth differently, but no less profoundly. In the summer of 1944, Lieutenant Saburo Sakai, one of Japan's most skilled and experienced fighter pilots, a man who had survived combat since the opening days of the war, encountered an American fighter unlike any he had seen before. It happened over the Philippine Sea during the Battle of the Philippine Sea, the engagement American pilots would later call the Great Marianas Turkey Shoot.
Sakai was flying a Mitsubishi A6M0, the fighter that had once seemed invincible, the aircraft that had terrorized Allied pilots at Pearl Harbor, Wake Island, and throughout the Pacific in 1941 and 1942. But by 1944, the Zero's advantages had evaporated. American pilots had learned its weaknesses, American fighters had closed the performance gap, and American industrial output meant that for every Zero Japan could field, America could field 5 or 10 opponents. On June 19th, Sakai climbed to intercept American carrier aircraft attacking the Japanese fleet. He spotted a formation of Hellcats, Grumman F-6F fighters, the Navy's standard carrier-based fighter, sturdy and powerful, but not particularly fast or agile. Sakai maneuvered for an advantageous position, using the Zero's superior maneuverability to slip behind one of the Hellcats. But before he could open fire, something flashed past him, a blur of dark blue metal moving so fast he barely registered its shape. It was another American fighter, but not a Hellcat. It was smaller, lighter, with a distinctive inverted gull wing that Sakai recognized from intelligence briefings, a Vought F4U Corsair. The Corsair pilot, Sakai never learned his name, executed a high-speed slashing attack, fired a burst from his 6.50 caliber machine guns, and was gone before Sakai could react. Sakai's Zero shuddered as rounds tore through the wing and fuselage. He broke off immediately, dove toward cloud cover, and barely made it back to his carrier. Later, in his memoir, Sakai would write about that moment with something approaching awe. "The American pilot did not try to dogfight me," he wrote. "He did not need to. His aircraft was so fast that he could attack and escape before I could bring my guns to bear. It was like being hunted by a falcon when you are a sparrow. The skill of the pilot mattered less than the machine he flew." The Corsair was not as aerodynamically refined as the Mustang. It was not as absurdly fast as the XP-72, but it embodied the same philosophy: speed as doctrine, speed as overwhelming advantage, speed as the product of an industrial system that could afford to build fighters with 2,000 horsepower engines and still produce them in quantities that made individual losses irrelevant. Japan could not match this. Japan's aircraft industry was still producing Zeros with 1,130 horsepower engines because more powerful engines required rare metals and high-octane fuel that Japan no longer had. Japan's pilots were still taught to value maneuverability over speed because Japanese strategic doctrine emphasized individual skill over material advantage, and Japan's military leadership was still issuing orders based on the belief that fighting spirit could compensate for technical inferiority.
By 1945, Japanese pilots were flying suicide missions not because they had embraced death as a cultural ideal, but because it was the only tactic that had any hope of success against an enemy whose machines were simply too fast to intercept conventionally. There was a moment late in the war when the philosophy behind American speed became visible in its purest form. It occurred not in combat, but in a factory, the North American Aviation plant in Inglewood, California, in October 1944. A Luftwaffe officer named Hauptmann Hans Gunther von Kornatzky, captured after bailing out over France, was being given a tour of American industrial facilities as part of a psychological operations program designed to demonstrate to prisoners of war that Germany had no hope of winning. Von Kornatzky had been an engineer before the war. He understood aircraft production. He had visited Messerschmitt and Focke-Wulf factories in Germany, had seen the Herculean efforts required to maintain production under Allied bombing, the women and forced laborers working in dispersed facilities hidden in forests and tunnels. What he saw at North American Aviation shattered his understanding of industrial possibility. The factory was enormous, a single structure covering over 1 million square feet, brightly lit with assembly lines moving at a steady, unhurried pace. Workers operated in shifts around the clock. Components arrived from suppliers across the country, precisely manufactured to tolerances that eliminated the need for hand fitting.
Fuselages moved down the line, accumulating wings, engines, instruments, armament, paint, and finally rolling out the door as complete aircraft at a rate of 1 every 63 minutes. Von Kornatsky watched a Mustang roll off the production line, watched a test pilot climb in and take off for a brief shakedown flight, watched the aircraft land 20 minutes later and taxi to a holding area where dozens of other Mustangs waited to be ferried to ports for shipment overseas. "How many do you produce?" he asked his escort through a translator. "This plant? About 150 per week," the escort replied. "We have other plants producing Thunderbolts, Lightnings, Corsairs, Hellcats, altogether maybe 3,000 fighters per month, plus bombers, transports, trainers." Von Kornatsky did the math in his head. Germany, at its peak production, had managed perhaps 2,000 fighters per month total, and that had required dispersing production across dozens of facilities, operating under constant air attack, cannibalizing resources from other industries. America was producing more fighters in 1 month than Germany could produce in 2, and doing it in bright, spacious factories that had never been bombed, with workers who went home to comfortable houses and full meals every night. "This is why we lost," von Kornatsky told his escort, "not because your pilots are better, not because your tactics are superior, but because you can afford to make your aircraft fast, and you can afford to build so many of them that speed becomes a systematic advantage. You do not need to choose between performance and quantity. You simply build both." The escort, a young army lieutenant who had never seen combat, did not fully understand the significance of the statement, but von Kornatsky understood. He had seen the secret behind the speed, not a secret of engineering, but a secret of philosophy and resources. American fighters were fast because American engineers were free to pursue speed without compromise, because American factories had the materials to build engines powerful enough to achieve that speed, because American training programs could afford to teach pilots to exploit that speed rather than compensate for its absence, and because American strategic doctrine embraced the idea that technical superiority was not an extravagance, but a necessity.
It was the opposite of everything von Kornatsky had been taught about efficient resource allocation and the primacy of will over material. And it had made American speed not just an advantage, but an inevitability. The symbolic object that haunted enemy pilots was not a weapon or a piece of equipment, but a sound. It was the sound the Corsair made in a dive, a distinctive high-pitched whistle produced by airflow over the oil coolers in the wing root. Japanese soldiers called it whistling death. They heard it from the ground, heard it in the seconds before rockets and bombs and machine gun fire tore through their positions, and they learned to associate that sound with the impossibility of escape. If you heard the whistle, it was already too late to run. German pilots had their own version, the scream of a Mustang's Merlin engine at full throttle, a sound unlike the rough growl of a BMW or Daimler-Benz. It was smoother, higher, almost mechanical in its precision, the sound of an engine that was not struggling but performing exactly as designed, with power to spare. When Luftwaffe pilots heard that sound closing in from behind, they knew they were being run down by something they could not outmaneuver or outrun, and the only hope was to dive for the deck and pray the American pilot broke off the pursuit. These sounds, these auditory signatures of American speed, became their own form of psychological warfare, more effective than propaganda, more demoralizing than casualties. They were proof that the war was not being fought on equal terms, that the industrial and intellectual systems producing these machines were operating on a different level entirely. And they kept getting louder. By 1945, the P-51H, the final production variant of the Mustang, could reach 487 miles per hour, nearly matching the XP-72's record. The F-8F Bearcat, a compact Navy fighter designed specifically to counter Japanese kamikaze attacks, could climb at 4,500 feet per minute and reach 455 miles per hour, despite being smaller and lighter than anything else in the American inventory. And the jets were coming. The P-80 Shooting Star, capable of 600 miles per hour, was already in testing and would have seen combat if the war had continued into 1946. The enemy knew this. Intelligence reports filtering back to Berlin and Tokyo in early 1945 painted a picture of American air superiority so complete that conventional air defense was becoming theoretically impossible. German jet pilots flying the Me-262 could achieve local tactical victories, could shoot down bombers and fighters in individual engagements, but they could not stop the formations of hundreds, could not prevent the systematic destruction of every strategic asset Germany still possessed. Japanese pilots flying obsolete aircraft cobbled together from spare parts knew they were not fighting for victory, but for time, for delaying the inevitable by days or weeks. Speed had become America's language of inevitability.
The epilogue to this story is not found in the war itself, but in what came after. On September 20th, 1946, a modified North American P-51 named Beguine took off from Chino Airport in California. At the controls was a civilian test pilot named Alvin Tex Johnston. The aircraft had been stripped of military equipment, fitted with an experimental propeller and equipped with extra fuel tanks. Johnston's goal was simple: break the international speed record for piston engine aircraft, a record that still stood at 469 miles per hour, set by a German Messerschmitt before the war. Johnston flew out to the Mojave Desert, the same landscape where the XP-86 prototype had screamed across Rogers Dry Lake 2 years earlier. He climbed to 25,000 feet, leveled off, and pushed the throttle to full power. The modified Merlin engine responded smoothly, and Beguine accelerated rapidly. 450 miles per hour, 460, 470. At 480 miles per hour, Johnston trimmed the aircraft carefully and held the speed steady for the required measurement period. When he landed, the official measurement confirmed 483.041 miles per hour, a new world record. That record would stand, unbroken, for more than 30 years, until the age of unlimited air racing produced even more extreme machines. But by then, the piston engine fighter was a historical curiosity, a relic of a war that had ended decades earlier, displayed in museums alongside muskets and biplanes. What remained was the philosophy that had produced these machines, the belief that speed was not merely a tactical advantage, but a moral one, a demonstration that free societies could outthink, outbuild, and outperform authoritarian rivals because freedom itself was an engineering advantage. That the marketplace of ideas applied not just to politics or commerce, but to the brutal calculus of warfare, and that in that marketplace, the systems that allowed engineers to argue and fail and learn and iterate would always, eventually, defeat the systems that demanded ideological purity and obedience to central planning. The American fighters that broke records and terrorized enemies during World War II were not simply faster because of better engines or cleaner airframes. They were faster because the society that produced them valued the pursuit of speed as an expression of liberty. The liberty to experiment, to compete, to waste resources on ideas that might fail, to reward success without punishing failure, to let a dozen companies try a dozen approaches and see which one worked best. This was the absurd secret the enemy could never copy, even when they captured the aircraft and studied their construction. The secret was not in the blueprints, it was in the system that produced the blueprints. And that system could not be replicated by force of will or dictate of authority. In the end, the whistle of the Corsair and the scream of the Merlin were not just sounds of engines, they were the sound of an idea, freedom, accelerating beyond the reach of tyranny. and tyranny, for all its momentary advantages, could never catch up.